Let's dive into some examples here. You see here we have a radical in the bottom of the fraction. So a trig substitution is implied as a reasonable technique. So I need to define a u and an a, bearing in mind that it should follow the model of the square root of a squared minus u squared, a squared plus u squared, or u squared minus a squared, all under radicals. All right, so this one seems to follow this model. All right, so I'll write it with the a first and then the u. The a seems to be a 4. The u seems to be an x. All right, so what we want to do is place, and this is kind of like a way of setting this up so that we don't really have to rely too much on the rules on the previous page. And that is set it up so that the missing side will be the square root of 16 minus x squared. All right, so let's say, for example, I put the x here and the 4 here. If I did that, then the missing side would be 16 plus x squared under a radical. That's not going to work. All right, it's close, but not quite. All right, so what that's telling me is that the hypotenuse needs to be a 4, and one of the missing legs has to be an x. All right, if I put the x here, then what I can create is one of our better trig ratios, and that is the ones without the cos. So I can create the sine ratio. Sine of theta would be x over 4. The missing side here would be the square root of 16 minus x squared. All right, so one ratio should be variable to constant. The other ratio should be radical to constant. This radical occupies the adjacent side. This constant occupies the hypotenuse. So the trig ratio that is the adjacent side over the hypotenuse is cosine. So cosine of theta is going to be equal to the square root of 16 minus x squared over 4. All right, so what we want to do is make some substitutions with this. Well, one thing I see kind of off the bat is if I multiply this both sides by 4, I get 4 cosine of theta is equal to the square root of 16 minus x squared. That's a direct substitution. So 16 minus x squared could now be replaced with a 4 cosine theta. But you see now we have a disagreement between variables. I got x's, dx's, but then I have thetas. I need everything to be in theta. All right, so what I'm going to do here is solve this for x and differentiate. So I'll have dx d theta is equal to 4 cosine theta. All right, so that's going to allow me to swap out a dx. If I solve for dx, 4 cosine theta d theta. Now there's other ways to do it, but this is the way I prefer to do it. All right, if you like a different way, a slight modification, go for it. All right, but now I can replace the dx, and I can also replace just the x itself. Because x and 4 sine theta are the same. All right, so 4 sine theta plus 3 over 4 cosine theta times 4 cosine theta d theta. Well, we get a nice cancellation here, 4 cosine theta into 4 cosine theta. So all I have to do is integrate 4 sine theta plus 3 d theta. Antiderivative of sine is negative cosine, so negative 4 cosine theta plus 3 theta plus c. Can't leave my answer in terms of thetas. They gave me a question in terms of x, so I got to give them an answer in terms of x. And so I'll do that pretty easily, actually, just by looking back at what we have. Well, I got a triangle here, and I'm just going to do a copy-paste job on the triangle. We also have it stated pretty explicitly what cosine of theta is equivalent to. But I'm going to pull this information here. Take a screenshot is what I wanted to do, because it's a printed triangle. I wouldn't be able to just copy paste it. Well, this looks alright, I guess. Alright, so based off of that angle theta, I took the triangle. I didn't take everything I needed with it. The hardest thing to write is the one thing that didn't come. 16 minus x squared. All right, so cosine adjacent over hypotenuse. So remember, we have a reference angle of theta. Everything is in reference to that angle. So we have an opposite, we have adjacent, and we have hypotenuse. All right, cosine of theta is adjacent over hypotenuse. So I'm going to have a negative 4 times the square root of 16 minus x squared over 4 plus 3 times theta plus c. All right, now that's kind of a tricky thing, because theta is the result of a trigonometric expression, but it in and of itself is not necessarily one. All right, so what I would do here is find a nice simple ratio. All right, I go to the triangle, and oftentimes, I mentioned this earlier, oftentimes it's something that's written. Oh, I wanted to copy the whole thing, get the image function on there. Oftentimes it's something that's already written. In this case, it actually happens to be the sine function, which is stated up here. Sine of theta is equal to x over 4, but I'm going to pretend that we don't have that information. So I'd look at it and say, all right, what's a nice simple ratio that I can grab from this triangle? I think the opposite and the hypotenuse. That's the ones that don't involve a radical. Right? So I would say, oh, let me grab the opposite, let me grab the hypotenuse. That's x over 4. Then I would say to myself, okay, what is that trig ratio? Opposite over hypotenuse, that's sine of theta. All right, if I just want the theta, then what I would have to do is find the inverse sine of both sides. In which case I would get theta is equal to inverse sine of x over 4. Now, no matter which one you selected, let's say you decided you wanted to go with cosecant, it still would have worked. You would have gotten theta is equal to the inverse cosecant of 4 over x. Or theta is equal to the inverse cosine of the square root of 16 minus x squared over 4. Whatever ratio you select is going to be right, as long as you carry out the process the right way. But the simplest one appears to be this one. All right, and so with a quick cancellation of a 4, we pretty much have it negative the square root of 16 minus x squared plus 3, that's not a 3, 3 sine, inverse sine, x over 4 plus c. So then we take a look at the next one, and you see that, you know, some of the ingredients are kind of along the lines of what we want. You know, we're looking for something that follows one of these patterns. We're not quite there because I don't see a radical. But this is kind of where you get a little cute. All right, I see a plus sign. So let's grab one that has a plus sign. Can I make this into something that involves a radical? Yeah, just throw a radical on it. That's a rule, right? Yeah, I'm just going to pop a radical over it. Yeah, why not, right? What the heck? I'll put a radical over it and then also square it. All right, so I just manufactured something that follows the form of a squared plus u squared under a radical. Even though it wasn't under a radical, I made it so that it follows that form. All right, so a would be 2, u would be x, right? So I want to place them on the triangle in such a way that the missing side would be the square root of 4 plus x squared. So if I put the x here and the 2 there, using the Pythagorean theorem, I'd get 4 plus x squared under a radical, and that's what we would be going with, all right? If it doesn't work out the first time, you just move it, swap the sides, move them around, and go from there. But as it turns out, this is the perfect way of representing it, because variable to constant, we have opposite, adjacent, tangent. Then radical to constant, you have hypotenuse to adjacent. That's going to be hypotenuse to adjacent is secant. So the square root of 4 plus x squared over 2. Now if I want to clean this up, I'd solve for x, differentiate, solve this one, the second equation, for the radical 4 plus x squared, and then make my substitutions. The square root of 4 plus x squared for, let me get the right highlighter here, so the entire radical, for a 2 secant theta. Alright, so I'll start with that. So I have dx over 2 secant theta squared. Then what I'm going to do is replace my dx with a 2 secant squared theta d theta. Okay, so we have a nice cancellation. Can't always guarantee that, but when it happens, it's really nice. So the integral of 1/2 d theta is going to be 1/2 theta plus c. So now I just have to pull a theta out of this. Alright, so what I'll do is I'll choose a nice convenient ratio. Like, for example, the tangent theta is equal to x over 2. That's a nice one. So I'll take the inverse tangent of both sides. And that'll give me theta equal to inverse tangent of x over 2. Alright, so now I know that my final answer ought to be 1/2 inverse tangent of x over 2, the whole thing plus c, and there it is.